Hello, 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 hello. Welcome back to linear algebra. Are you feeling linear? All right, let's check Anki. Anki is a flashcard system that's optimal for spaced repetitions. And there are no Anki cards due right now. All right, very good. And we're all good here. What did we learn yesterday? Well, I know we were reading about complex numbers. And, okay, complex conjugate, that's something we learned. What is the complex conjugate? Well, the complex conjugate is also known as the conjugate. It's basically you reverse the sign of the imaginary part of a complex number to get a conjugate. So therefore, a real number's conjugate or complex conjugate is just itself. And if a number's complex conjugate is itself, then it's a real number. So it's if and only if, bidirectional arrow. Complex plane, we learned about that. Complex plane is basically just the Cartesian coordinate plane, two-dimensional plane. However, okay, right. It's for plotting complex numbers. The y-axis and the x-axis, right? The x-axis, I believe, yes, this is the real axis, and the y, that is the imaginary axis. So a complex number in the form of a plus bi, you can get a plotted point or a location of the tip of a vector based on a comma b, just like x comma y. Okay? Cool. We are getting into some formulas based on the definitions of reciprocals and absolute value modulus. Okay, so the absolute value, hold on. Yeah, absolute value of a complex number, or also known as the modulus of a complex number, that is the length of the diagonal the length of the vector. It's the length of a vector on the complex plane. It's also known as the modulus of a complex number, right? How do you find it? Well, it's basically, you multiply the complex number by its complex conjugate. And that ends up being a non-negative real number. Essentially, it's a squared plus b, or square root of a squared plus b squared, right? Imaginary or real part squared plus imaginary part squared. Take the square root of both of that, or that all, and then you get the length of the diagonal, the absolute value or modulus of complex number. One other thing, we got the bar. So complex number, if you denote the complex number as a symbol, say z, well then the complex conjugate, that's denoted as z bar, so a bar over that symbol. So we know how to find the modulus, or the absolute value of the complex number. All right. Okay. Reciprocal. What is a reciprocal? It's basically 1 over the complex number, or the number in general. So it's just 1 over, or the number to the power of -1. That's how you find the reciprocal. Okay? Now we're talking about some equations based on the definition of reciprocals and complex conjugate. So a complex number times its reciprocal is equal to 1. That's the definition of the reciprocal. So then if we take both sides of this and multiply it by, what would that be? Z bar or the complex number, absolute value of the complex number. So then this side's going to be the absolute value of the complex number. This side's going to be 1 over complex number times complex number bar. And we know that complex number times complex number bar is a squared plus b squared, the square root of that, square root of a squared plus b squared, aka the absolute value of the complex number. So now we've got 1 over complex number times the absolute value of complex number equals complex conjugate of the number, which we know that makes sense then, because if we multiply both sides then by the complex number, that will cancel out the reciprocal, and then over here that will get absolute value of complex number. So absolute value of complex number equals absolute value of complex number. I don't know why. I don't know why they're telling us that necessarily as of yet, but I guess we'll find out pretty quickly here. Let's make sure I got everything. Okay, cool. Complex number multiplied by, okay, cool. Yep, cool. Okay, reciprocal is also known as the multiplicative inverse. Cool. If z does not equal 0, then the reciprocal. All right, okay, so that the reciprocal, it needs to be non-zero for it to be equal to 1 over the number. Okay. All right. C and r squared are similar and about the same. That is the complex number system, and r squared, I'm not sure exactly what r squared is. Okay, so here's the formula. 1 over z equals z bar divided by absolute value of z squared. How do we get this? Well, if we times both sides by so we got the definition of the reciprocal, right? 1 over z times z equals 1. Multiply z bar by, because of the complex conjugate by both sides. I already said I thought I did this. This is then becomes absolute value of z. This becomes z bar. This becomes z, absolute value of z. No. This becomes z bar. Then you times z, absolute value equals absolute value. Okay. What should you attain by multiplying both sides by z bar? Oh. So z times z bar does not equal absolute value of z. That actually equals the square root. Yeah, the square. Okay. So it equals z, the absolute value of z squared. Okay. So we times both sides by z bar. That's going to give us 1 over z times absolute value of z squared equals z bar. Okay, and now then we divide z absolute value of z squared divided by both sides. That'll cancel out over here. So now you've got z bar divided by z squared equals z over 1. Okay, cool. I don't know why that we need to know that exact equation. 1 over z equals z bar over z absolute value of z squared, but whatever. All right, I'm going to continue reading now, and then I will be back to recall. All right, guys, I don't know how I only have 5 minutes left. I just must have spent a lot of time reading. I tried to digest these formulas. So what did I learn? Basically, all those formulas they were presenting and the manipulations of these definitions of reciprocal and complex conjugate, it was really to show how to divide complex numbers. And simply, the way to divide complex numbers, you're just going to want to take, assuming it's z1 divided by z2, and z2 is not z2 is not 0, then you just multiply both the numerator and denominator by z2. Cool? All right. So that's dividing complex numbers. Then we get in polar form. And in polar form, this is another way of writing a complex number. So when we're in the complex plane and we graph this vector, the angle that the vector and the positive x-axis form, or positive real axis form, is, I don't know this Greek symbol, but I'll just call it theta for now. It's not theta, it's a different Greek symbol, but this angle is called the argument. And the You can multiply, or you can subtract or add 2 pi to any of these 180 degrees to these arguments, and keep and getting the same shape but a different degree. So the principal argument is the the principal argument is the argument between negative pi and pi. And then polar form. So if we say that the absolute value of z is the length of the vector, well, then we can say that a equals cosine, or a equals, the real part equals the absolute value of z times the cosine of that angle, and that is just a little bit of trig. And then for the imaginary part, we can call it b equals the absolute value of z times sine that angle. And so the polar form of a complex number is you're substituting these values. A equals absolute value of z times cosine angle, and b equals absolute value of z times sine angle into the original complex number form of z equals a plus bi. So you're going to get z equals cosine, or you're going to get z equals absolute value of z parenthesis cosine angle plus sine angle times I, and then all of that within that parenthesis that's getting multiplied, that you can distribute that absolute value through. All right, there we go. We also got some theorems for how the nature of complex conjugates work, as well as some reciprocals. But yeah, I think we got the idea, the general idea. We're going to keep moving now. We've got 2.5 minutes. I'm just going to read this example polar form of a complex number, this little box here, and then I'll be back to finish off today. And it looks like after this, we're going to have one more section, three more sections, but only about 2 pages left in this Appendix B, and then we'll be in Section 1, Part 1, which I've been looking forward to, so I'll be back in a second. All right, that's it for today. It was just a little box about how to find the polar form of a complex number. So that's it for today. Maybe 1 or 2 days left for Appendix B, and then we'll be into the text. Chapter 1, Section 1, which I'm very excited for. All right, talk to you guys later. See ya.